Now, with a 2 channel filter bank, free of aliasing, right, we can write x hat of z to be some t of z times x of z, where t of z is this transfer function given by 1/2 h naught of z f naught of z plus h1 of z f1 of z, and this is called the distortion transfer function. Why? Obviously, as the name suggests, the signal x of z is distorted by this transfer function t of z. Now, we apply the conditions for f naught and f1 through the alias cancellation equations, and we simplify this as t of z is 1/2 h naught of z h1 of minus z minus h1 of z h naught of minus z. Okay. Now, when I evaluate t of z at z equals e j omega, I get some magnitude of this transfer function, and then I have some phase phi of omega x of e j omega, right. So, I just rewrote this transfer function as having some magnitude response, having some phase response. Now, unless modulus of t of e j omega is a constant, some d which is not equal to 0 for all omega, we have magnitude distortion, right. Unless this is some constant, if I know it is a constant gain, then I can just attenuate that gain. I can just use some amplifier to just either adjust my gain accordingly if it is a constant gain. If not, if the gain varies across frequencies, then I have amplitude distortion. Now, unless phi of omega equals a plus b omega, I mean is of the form, unless phi of omega is of the form a plus b omega, x hat of e j omega suffers from phase distortion. This is very, very important, this phase distortion, because the signal can have different phases for different frequencies, and you have to really compensate them very carefully. That means, if you have a signal, this will have different frequency components, and imagine that you are sending the signal through a bank of filters, and each filter or each frequency is suffering some distortion in its amplitude and in its phase, right. If that means the delay at the output when you would get the signals would be different for different frequencies, that is the physical meaning of phase distortion, right. So, different frequency components will arrive at different times at your output if you have a phase distortion, and it is important to eliminate this. So, these are two major points. Okay. Now, we will go one step further. Let V of z is be equal to h naught of z times h 1 of minus z, and V of minus z is basically h naught of z, h naught of minus z, put a minus here, h naught of minus z times h 1 of z, right. This is just minus z here. Okay. So, now T of z is 1/2 of V of z minus V of minus z. So, this is what we have. Now, with this we can see that if you have a z and a minus z of z square and a minus z square is the same, z power 4 and minus z power 4 is the same. So, therefore, you can think that all the even powers get cancelled here and you will be left with odd powers, right. So, T of z has only odd powers of z. Therefore, T of z can take this form z power minus 1, that is you factor out a unit delay times some polynomial in z square, right, because you will have a z cube, z power minus 3, all the odd components you will have. So, just factor the delay out, the rest of it would be even, right. So, there will be some polynomial in z square, and I think an inspection would tell you that modulus of T of z has a period of pi instead of 2 pi. Just observe this power here. If it has to be periodic, is e power 2 j omega, right, j to omega plus. So, what would you do if you were to translate this by a period t, and that has to be basically pi, right, and just because of the power 2 here. So, we have a notion for perfect reconstruction. So, for the perfect reconstruction property, T of z has to be of the form C z power minus a naught, that is it just suffers from some gain C and some delay. Perfect, and the ideal case is when n naught equals 0 and C equals 1, that is an ideal situation, right. A less ideal situation would be to have some gain and some delay, because you can compensate. So, this implies that x hat of n is basically some delayed version of the input. Now, let us consider the quadrature mirror filter bank system. Suppose h 1 of Z that is if it satisfies the quadrature mirror filter property, then H1 of Z is H naught of minus Z, which implies H1 of Z is a good high pass filter if H naught of Z is a good low pass filter. If H naught of Z, your base filter, is a very good low pass filter with good properties, then H1 of Z is a very good high pass filter, and it is obvious to see that the magnitude of H1 of Ej omega is basically magnitude of H naught of Ej pi minus omega, right, and that minus 1 accounts for this factor. Now, all the filters are completely specified, as we discussed earlier, that if you have a filter H naught, then you get H1, F naught and F1. Now, the distortion function in this case is easy. T of Z is basically 1/2 of H naught square Z minus H1 square Z. And then if we can simplify this as 1/2 of H naught square Z minus H naught square of minus Z. So, in terms of one base filter H naught of Z, we can get the distortion function for a quadrature mirror filter bank. So, I think the sequence of steps were as follows. We get the distortion function after we force the alias cancellation conditions, right. Once we force alias cancellation, we will have an equation in terms of H naught and H1 in our distortion function, and then we invoke the QMF property, and then we can eliminate H1 as well, and we get in terms of purely H naught. So, I think this gives us an idea that we can start with this distortion function, and we can basically figure out how we have to design these filters H naught, we have to design this filter H naught of Z that can eliminate amplitude distortion. Okay. Now, the phase is a little more interesting. So, let us just get towards the phase distortion. For phase distortion, so let us consider the filter H naught of Z to be of this general form H naught of n Z power minus n, n equals 0 to n. Let us assume that H naught of n is real. So, we also let H naught of n equals plus minus n minus n. So, this will ensure it is linear phase, but for low pass property you have to remove the negative, because if you have a negative sign, it is implying it could be a band pass or a high pass, right. So, all the coefficients should have the same sign, that is one of the conditions. So, H naught of n is basically H naught of capital N minus small n. Okay. So, with this we can simplify things a little further. So, we can say H naught of Ej omega is of this form e power minus j omega times some linear function of omega. It could just be a constant times r omega, and you can simplify this to this form. T of E j omega is e power minus j omega n 1/2 of that times mod h naught of E j omega square minus 1 power n magnitude of h naught E j pi minus omega square. This is your distortion function. Now, if n is even, this becomes 1. So, this would just vanish. T of E j omega reduces to 0 at the frequency omega equals pi by 2, leading to severe attenuation. So, I will leave the simplification as a homework exercise. I mean, this simplification of how you have to arrive, how you would get this T of E j omega in this form, I will leave this as a homework exercise. Okay. So, with this there are some other details that we have to understand regarding minimizing the residual amplitude distortion. Right, we eliminated the aliasing error, then we looked at the phase distortion, right. We said we want to have linear phase, we started with an FIR filter, we ensured that it is the symmetric, it is mirror symmetric, right. So, now with the mirror symmetric property in mind, then we want to we simplified it further to get the overall distortion function, and that distortion function could have possibly an amplitude distortion, because it is distorted across frequencies. The amplitude is distorted across various frequencies, right. So, let us see in a little bit of careful detail what this is about. So, if you think about how this h naught of E j omega square magnitude plus h 1 of E j omega square, how this looks, ideally you might want it to be at 1, but at the quadrature frequency, which is at pi by 2, you can have a blip up or you can have a blip down. And our goal would be to have the magnitude of h naught of E j omega square plus magnitude of h 1 of E j omega square to be 1 approximately. Is equal to 1 is ideal, close to 1 is approximate. And what do we need to do? If this is our constraint, we have to choose the coefficients of our filter h naught of z such that this relationship holds, right. So, h, of course, if you use QMF property, h 1 can be expressed in terms of h naught, we know that. So, everything can be recast in h naught itself, and then if we recast it in that framework, then we have to design the filter, that is we have to choose the coefficients of this filter H naught of z such that this is equal to 1 approximately, but that is hard to get. Already we invoked some symmetric property for the filter, we ensured it is linear phase, right. We took care of all these other constraints. Now to eliminate this distortion completely would be very hard. So let us formulate an objective function that possibly helps us to drive choosing our filter coefficients appropriately. Okay, let us assume phi is of the form alpha phi 1 plus 1 minus alpha times phi 2 with 0 less than alpha less than 1, and let us define the functions phi 1 and phi 2 as follows. Phi 1 basically goes from your stop band to your Nyquist integrating this function, that is this is the magnitude square distortion and you are integrating it across all the frequencies. So, you are basically getting the energy, right, you are getting the energy in the tail from the stop band to pi, and then suppose if you want, if you choose phi 2 as summing up the energy over the residual, that is 1 minus magnitude of H naught of E j omega square minus, so I will now invoke the QMF property H naught of E j pi minus omega square, and this if I were to integrate across all frequencies, then I would want to choose H naught of n is minimum over all phi, minimum or over all H naught of n, minimum over all H naught of n, this objective function phi. That means if I choose alpha to be 1, I only minimize the tail energy, right. If I choose alpha to be 0, I look at just this distortion, that is the H naught and H 1 magnitude square should deviate from 1, that residual square energy I want to minimize over all frequencies. So, this is like your error that you have, error square is what you set up here and I want to minimize this error square. Okay. So, these are some objective functions, and I mean one such function is this. So, this gives you a gamut of choosing your alpha just from the tail, that is from the stop band to pi versus looking at the entire band from 0 to pi, and choosing this sort of objective functions leads us to an optimization procedure, and this procedure was done by Johnston in the 1980, and these are called Johnston filters. So, if you designed your base filter with this objective function in mind, then it gives rise to an optimal low pass filter under this constraint for this objective function, and they are called Johnston filters. Okay. So, this completes our work on analysis of the 2 channel filter bank for alias cancellation, for phase, for minimizing the phase distortion, and then for minimizing the amplitude distortion. So, you have to keep in mind, first you start with the alias distortion, you figure out how your synthesis filters have to be chosen to eliminate aliasing distortion. Then to simplify your design, you assume quadrature mirror property, so that given a base low pass filter you can construct the high pass filter as well. Then you analyze the magnitude distortion function, you analyze the distortion transfer function, and from that you simplify further to look into the phase distortion and amplitude distortion, and then construct filters that can minimize these distortions. Okay. So, with this we are done with the analysis of a 2-channel filter bank, and we will extend this further towards m-channel filter banks, and then we will study the properties of those filter banks. We will stop here.